So thank you all for coming. I'm very glad to present you this joint work with Philippe, Antonin Bergeau, who is here, and Marc Melitz, on the impact of exports on innovation. So, I should have checked this before. Okay. Is there a link between export and innovation? And in particular, is there a link from exports to innovation? The literature has emphasized one main mechanism so far, it's the market size. When a firm has access to a bigger market size, the innovation rent it can extract from this market increases, so it has a bigger incentive to innovate. And the literature has also shed light on the positive effect of competition on innovation. And we will see how we can reconcile these two effects. So, is there a link? Yes. When we rank manufacturing firms according to how much they export, so it's the centile of exports, or centile of the distribution of exporters, we see that the more a firm exports, the more likely it will innovate. The centile 0 here contains all the firms with 0 export, and you see that very, very few of them innovate. And the innovators are very concentrated in the higher tail of the export distributions. So export and innovation performance are very highly correlated. This is true at the extensive margin. So an exporter is more likely to innovate and an innovator is also more likely to export. But it is also true at the intensive margin. A big exporter will be a big innovator and vice versa. So is this link causal, and in particular from export to innovation? And if so, what is the driver behind this? So in a nutshell, we'll do 3 things. Well, we merge 3 exhaustive firm-level datasets on French firms, from customs, from patenting, and all the administrative tax data. And we see how the expansion of the export market will influence its patenting. And to be sure of the direction of causality, from export to innovation, we construct a firm-level export demand variable. And this variable will respond to aggregate conditions in a firm's export destination, but it will remain exogenous to the decisions of the firm. And in particular, its decision to export in this or that country, this or that product. So that when we see a firm exporting with expanding export market innovate a lot, we can be sure that it's not because the good innovators choose wisely their export destinations. So what we show, first, that the firm's patenting responds positively to a positive export demand shock. So you can see here, on the x-axis, it's our export demand variable that I just described, and on the y-axis, it's the number of patents. So when a firm has a big export demand, it has also higher number of patents. But we also show that this effect is substantially stronger for firms that are more productive initially. So when we break down this relationship between firms with initial productivity below the median in blue and above the median in red, you see that the response is almost flat for firms below the median, and it's much stronger for firms above the median. So we'll show how this can be reconciled with 2 different effects. First, a market size effect and also a competition effect. The market size will increase innovation for everyone, and the competition effect will reduce innovation, but much more for the firms which have low productivity. And we also show that the competition effect dominates for the less productive firms. So I'll go quickly on the literature. You have of course, the literature linking trade, innovation, and growth. You also have a recent literature on import innovation and productivity growth. And of course, the trade liberalization episodes are good instruments to see the impact of exports on innovation. Now, on the model, we'll only consider the French exporters. So consider a French firm exporting to destination D. You have L consumers in that destination, and their income is normalized to 1. And these consumers, they spend eta F of their income on French goods. Now, if we assume a quadratic utility function for the representative consumer, you get the inverse residual demand function, so the price of the good as a declining function of Q, the quantity. And here you have, it's also a function of lambda. It's the marginal utility of income, and it's a very important parameter, variable in our model. It will measure the competition. So I'll present you graphs and results in this section theory with very simple functional forms, but all our results hold with more general functional forms. So regarding the firm optimization, it chooses its output, Q, and it knows it has a fixed cost of producing, marginal cost of exporting C. So it simply maximizes its expected profit. And it leads to equilibrium profit and sales that we have here. Now, this model was largely taken from Maria Melitz and Intervenant, and we introduce innovation in this model. So a firm has the possibility to invest in innovation, and doing so, it will reduce its baseline cost, so it will become more efficient. And an investment will have a quadratic and linear component that you have here, and it will reduce innovation by epsilon k. How does the firm choose its optimal amount of innovation? Well, it simply maximizes its profit. So it's L, the size of the export market, times the profit that it makes on this market per consumer. And you see that it will do so knowing that its cost has decreased when it invests K in innovation, and minus the expected cost, the cost of innovation. So the first order condition, when we derive this with respect to K, leads to the second row equality, where we have the marginal gain from one more unit of investment in R&D is equal to its marginal cost. And we'll see in a minute that there can be a corner solution. So for firms which have too high cost, initially they will choose to do no R&D. Okay. You see that this equation is the equality of two linear functions, so linear in K. So it will be very easy to solve. Graphically, this is this. So the marginal cost is linear, and the intercept is Ci. You can see right here. And the marginal gain is also a linear curve with a different intercept and different slope. So as long as the marginal gain is above the marginal cost, the firm will want to invest more. So if you're on the left of the graph, the firm will want to increase K, its innovation. If you are on the right of the graph, the marginal gain is too low compared to its marginal cost, so it will reduce its innovation. So the equilibrium innovation will be the intersection of the two curves. And the second order condition ensures that the slope of the marginal cost is higher than the slope of the marginal gain. Otherwise, firms will end up doing infinite R&D. Now, comparing two firms two firms differing in their initial cost, you see that they have the same cost. So the right-hand side is the same. The marginal cost will not change, but the left-hand side is different, and only the intercept changes. The term in K, which is epsilon lambda times the ratio on the left, will be the same. So two firms with different costs will have the same slope but a different intercept. We can see it here. The blue curve will be the efficient, the blue firm will be the efficient one, and the red one will be the less efficient one with higher cost. And we'll see right away that the more efficient a firm is, the higher the innovation it will take. And we also see that firms with too high costs, so for which the intercept falls below CI, will do no R&D. So you have a corner solution here. The level of competition in the model is endogenously determined. How is it determined? It's the conjunction of two conditions. First, a zero cutoff profit conditions. It simply states that the marginal exporter makes a profit which just covers the fixed cost of exporting F. And the second condition, in the short-run equilibrium, it is a budget constraint. So N, the number of exporters in that destination, is fixed. And it simply states that all the revenues that the firms gather in this export market is equal to what the consumer in this market spend on French goods. And we can replace that with a free entry condition in the long run. So comparative statics, how do this equilibrium innovation change when the market size increase or when competition increase? So an increase in the market size will increase both the intercept and the slope of the marginal gain, and the marginal cost will never change. So it's plain and simple. For all firms, innovation will increase because the new curve is above the old one. This is the market size effect. And the competition effect, so an increase in lambda, will have another impact. It will decrease the intercept, but it increases the slope. And it's easy to show that the new curve will be below the old one, at least until it crosses the marginal cost. So that for all firms, an increase in competition will reduce innovation. But we'll see that it will reduce it more for firms which have low productivity. Why do we see that? It's because the intercept reduces much more for firms with high costs. And another interesting thing is that if the firms have very low productivity, they can even stop R&D because the competition has increased. Indeed, I almost plotted the marginal stopper here. If the new intercept falls below CI, the firm will choose no R&D. Now, the model also, I told you that lambda was endogenously determined in the model. In fact, it's an increasing function of the market size. So when the market size increases, the competition increases. So when you have an increase in the market size, in fact, you have two effects. First, a direct market size effect, which increases innovation for everyone. And then an induced competition effect, which decreases innovation, but it decreases much more for less productive firms. So in the end, what do we get? An increase in the market size will increase innovation for the most efficient firms, so for the blue firms, but it will decrease innovation for the low productivity firms. Now, on the data, we use three main sources, exhaustive sources on French firms. First, the patent data, then the firm-level accounting data. So it has many information filed by the firm to the fiscal authorities, including the number of employees, its sector, its export sales, and also the exports data from, and we'll use data from 1994 to 2012. Okay, merging data with firms in France is usually very easy because you have a unique identifying number for each firm. But the patent data doesn't come with that number. It comes with the firm name only. And the firm name has many flaws in it. You have differences in the spelling of the names. So it's very difficult to link patent data to the rest of the firm data. So to do that, we, with co-authors at the Banque de France, we computed an algorithm to try to see, to match at best the name that we have on the official INSEE repertoire and the name that we have on PATSTAT. And we also use BASI, which has all the bilateral trade flows from every country to all countries in the world at a very disaggregated level to build our demand variable. Now, we restrict our sample in a few ways. So first, we work with firms with more than 10 employees because for computational reasons, we couldn't do the matching between PATSTAT and Sirene for firms with less than 10 employees. Then we also focus on private firms, and we also, our main specification will be on the manufacturing sector. But all our results are robust to the non-manufacturing sector as well. And in the descriptive statistics I'll show you now, we define an exporter as someone who has exported at least once during our sample years, and an innovator will have innovated at least once in our sample years. So, this is the Lorenz curves for manufacturing firms in 2007. So it's simply the cumulative distribution of the firms. We don't see much in this picture, so I'll show you a zoom on the 5 first percentiles of the distribution. What do we see? It's that employment is the less skewed of the of the distribution. Then you have sales and exports. So we already knew that exports was much more skewed than sales, but what is maybe newer is that patenting is also a lot more skewed than patenting. You need the top 1% of the firms, when we rank them by size of sales, they account for 50% of sales. When we rank them by export, the top 1% explains 2/3 of exports. And when we rank them by patenting, the top 1% explains 91% of patents. But this picture does not capture the overlap between export and innovation. So to do that, I have some very simple descriptive statistics. What do we see from this table? Okay, first, it's that exporters are much bigger than non-exporters. You see they have much higher employment here than this. They have much higher sales, and they have much higher value added as well. But this is not really new. What is maybe newer is that innovators are very highly concentrated in the exporters. You see, you have only 6% of innovators which have never exported. What is also interesting is that among the non-exporters, innovators are not that different than the rest of non-exporters. They have about the same size. However, there is a massive difference among the set of exporters between the innovators and the non-innovators. They are really much bigger. They have higher employment, higher sales, higher value added, and they export more and to more countries. To quantify a bit more this, it has become common in the literature to show premia. So this table presents a knowledge regression from a firm variable. It's on the x-axis, on the dummy variable for exporting, so it's on the upper table. And you can have covariates. So the first column adds no covariates. The second column adds the control for a two-sector fixed effect. And the third column adds this sector fixed effect plus the log of employment. So if I take this third column, it says that if you take two firms in the same sector and with the same number of employees, an exporter will have sales 51% higher, it will pay wages 12% higher, and it will be more productive by 20%. So exporters are really bigger and more productive than non-exporters. Now we want to look at the additional premia of innovating. So we focus on the subset of exporters from this table, and we look at the additional premia of innovating. And what do we see is that among this subset of firms which are already bigger and more productive, the innovators are really even more bigger and more productive. So sales are 22% higher, they pay higher wages, they are more productive, and they export much more and to more countries. Now, I come to the empirical strategy. So we follow Meyer, Melitz, and Ottaviano, and we construct a variable which predicts the export demand that a firm will face, but it will remain exogenous to its decisions afterwards. So the idea is, if you take a firm F, which exports product S to destination G at T0, then all the evolution of the imports of that country for that product will be a good proxy for the demand faced by the firm. So formally, this is this variable that we compute. I'll describe it from the right. M, it's the country J's imports of product S from the world except France at T. We exclude France to strengthen the exogeneity of this variable with respect to the firm F. And so the ratio just next to log M simply weighs the importance that each market has for the firm. And you have the first ratio, which is the export intensity, so the ratio of exports over sales. It simply states that a firm with only 10% of its sales exported will be less impacted by what's happening on its exports than a firm exporting 90% of its sales. We also construct similar variables using the country's GDP or the imports aggregated at the industry level. Okay. So what do we do precisely? We will always use firm fixed effect in our regression. So we'll use the within firm information, and we control for any sector level changes with sector time fixed effect. And the main regression will be this one. So the left-hand side variable will be the accumulated stock of patents from 94. And the demand will be the one I just presented. And then we also consider the interaction of this demand with the decile of productivity of the firm, the initial productivity of the firm, computed at the sector level. Before I show you the table, graphically we come back to this graph. So on the x-axis you have the export demand and the stock of patents. I have taken out the firm mean in each variable, so it's very close to our regression. So you see that you have a clear positive response of patenting to the demand faced by the firm. And again, when we break down by firms below the productivity, below the median of productivity and above the median, you see the response is much stronger for firms above the median. Quantitatively, so you see that the decile variable varies from 0 to 9, so the coefficient on demand can really be interpreted as the effect on the firms in the lowest productivity decile. So it's negative. What does it mean? It means that relative to the sector, a firm in the lowest decile will introduce fewer patents when its demand increases than the rest of the sectors. So I'll show you, so the first three columns are with the left-hand side as the stock of patents, the last three columns are the stock of citations, and I'll show you the three dimensions that we computed, so at the product level.
Excuse me, Mathieu, it's compared to the mean, because otherwise the stock cannot never go down. It's compared to the mean of everybody, no? The negative.
Yes.
It's compared to the mean.
Of course, yeah. Compared to the sector mean. The second column is the industry level demand variable, and the third column will be the demand calculated at the GDP, at the country level, so with the GDP variable. And we see that they give a clear picture with the same signs and the same magnitude of the coefficients. So to understand a bit better what does it mean in terms of number of patents, imagine you have a shock of 1% of the mean demand variable. Then the firm in the lowest decile will introduce 2.9 fewer patents than the sector in which it is. Then each additional decile increase will increase the response of patent by 0.9 patent, so that the firm in the top decile will increase patent by 4.7 more patent than its sector average. Now, I restricted here the coefficient on this regression. I restrict that each additional decile has the same effect on the patenting. If I don't constrain this anymore, so if I have a different coefficient for each decile, we see that below the median, firms will have a response which is negative, and above the median, firms will have a response which is clearly positive. Again, it's relative to the sector. We also explore an alternate strategy.
It speaks to a competition effect, in fact, because if you only had a market size, you would see that all react positively. And the fact that you have some, that's what really speaks to the competition.
Yeah. We also explore an alternate strategy in long differences. So what we do is we take our full sample, we divide it in two equal periods, and we consider each period as one gigantic year, so we aggregate everything into each period, and we look at the difference between period 1 and period 0. So this is the regression that we have below. It's the new patent introduced in period 1 is regressed to the increase in the demand size, and the increase in demand size interacted with the decile of productivity, and we can now control for the decile of productivity. So you have now only one observation per firm. And the results, they more or less confirm what we had. So the main coefficient is the interaction between the demand and decile. It's very positive and significant. The effect on the lowest decile is no longer significant, but it remains negative. And you also have a positive effect on, of the decile. Okay. Now, why do we use patent and not R&D measures? First, it's because you have a data issue. Patents are exhaustive. If you firms have to file the, we have all the patents filed by the firms. On the other hand, data on R&D will be from a survey, and it's not exhaustive. The biggest firms are sampled every year, but the smallest firms are sampled only once in a while. So you have many gaps in the data. This does not seem to be too much of a problem because our regression with our stock of patents, but on this subsample, is still gives still the same coefficient. So it's column 2 here for the stock of patents, for example. It's exactly the R&D sample. However, you have first a theoretical problem is that you would use the input of innovation, so R&D, instead of the output of innovation, the patents. So you would bias our results against the most efficient firms doing this. And also, when we use the R&D variables, we don't find any significant results. And we are not sure about the conclusion yet, but we think it may be related to the fact that we don't have enough within-firm variation with these variables. So our framework would not be suited with these variables. So to wrap up in a nutshell, we show that the firm's patenting responds positively to a positive export demand shock, but that this response is substantially stronger for firms that are initially more productive. And we also show that the competition effect dominates for initially less productive firms. Now what we'd like to do is show the competition effect differently, and also look at the extensive effect of trade on innovation, so look at the entrance into innovation. Thank you.